Let's start this event. Hi, I'm Santosh. I'm a co-organizer of Let's Talk Spatial. We have Aman and Thiago with us. They are also an organizer from Let's Talk Spatial. I'll just give a brief of how Let's Talk Spatial started, and then we will have it from the Rashid, who is the founder of GalaxEye, and then we will continue the technical presentation. So firstly, I'm really happy that many of you turned up on this Saturday morning, taking time in a busy schedule for attending this event. Okay, so Let's Talk Spatial, we four, me, Aman, Thiago and Amrut, last year we just met and thought, okay, we don't have a community for geospatial. So why don't we create one where we will meet every month to discuss their expertise. We want to know what is happening in their stream, particularly in SAR or in the development of geospatial libraries. So we thought of doing it, and from September we are doing it, and this is the 9th Let's Talk Spatial event. So we are really happy. Next Let's Talk Spatial is going to be the 10th one. Today's theme is focused on SAR. So all the presentation and everything, you are going to see it based on the SAR data, and we are really happy and thankful to the GalaxEye team, and we will like to have it from Rashid, what GalaxEye is doing, a short introduction.
Check. Yeah, so first of all, I welcome you all to our office, to GalaxEye. And thank you so much for showing this much enthusiasm to attend this event on a Saturday morning. Yeah, it's been, I guess, quite a while since our team started attending Let's Talk Spatial events. And so I remember back in December, right, was an event which we attended, and we actually found it pretty useful, and we were feeling very inclusive as a geospatial team, that we were not able to communicate with more folks or connect with more like-minded folks in the same city, and that's where Aman and team kind of organized these events, and which helped us a lot, right? So from that moment itself, we were kind of committed to do something for this community, and at that time we had just taken up this office, rented this office. It had been 2 months. The interior and everything was not done. It took quite a while. Right, but now we are finally here, and we got an opportunity to give something back to you guys, right? So please make the most out of this opportunity. This is a very special group to us. Just talk a little bit about GalaxEye as well. So GalaxEye is a space tech company. We are a seed-funded space tech company, and what is so special about us is the sensor that we are trying to build. It's a combination of both high resolution multispectral and high resolution radar data, right? The sensor is what we are calling as, okay. So we are calling this as Drishti sensor, which is our IP, and our satellites are going to carry our sensor into space next year. And yeah, so that's kind of what our team does. And yeah, if you guys have any questions for me, please feel free to reach out, feel free to connect, and yeah, all the best. Make the most out of it.
Santosh, I think we should turn that light on. Is there a light here?
I know, then go on and visible.
It's not visible.
Even now, I think this light we can turn on. This row.
Rakshit, can you turn on this light?
Thank you, Rakshit, for the introduction of GalaxEye. Okay, so now I will just brief the agenda for today. So we will have one presentation, and then we will go for a break and a networking session where we will introduce each other, and then we will have 2 more presentations, and after that we will have coffee and network and then discuss. So this is the simple agenda for today, and we have an restroom over there. Feel free to use it in case you need. Okay. So today's first presentation is from Samyukta. She is a data scientist with a strong passion for geospatial analysis, remote sensing and GIS, with experience in various research organizations and industries. She specializes in leveraging the tools like Google Earth Engine for geospatial data processing, analysis, and visualization. She is currently focused on developing automating pipelines for crop classification and yield estimation as a part of global data science team at LDC. Let's welcome Samyuta for her presentation.
Hello.
Yes.
Hello everyone. My name is Samyuta Srivastav. I'll talk about in general the geospatial community, not INSAR, but almost everything based on my experience.
You just turn it. Just one second.
Wire.
I think it's fine.
Just turn the screen.
Yeah, sorry for the disturbance.
Okay, so I'm from geospatial background. I'm not a coder from the start, but I learned coding using Google Earth Engine, and it is one of the platform which I find it's very versatile. It has a limited number of APIs, so like for the beginners it's very good, and we can use it to like complete a project on one go and show it to the client using the UI. You don't need a coding background, or you don't need any other coding other than the geospatial data and knowledge which you have. So personally I find this open source very useful in geospatial community. I'll show you.
People won't even be able to see it.
Okay.
Yeah. Sorry. Yes. Yeah.
Can you keep it here, like to the audience?
Okay, so I'll show you through my experience of what is currently going on in geospatial community based on this application. There are various other applications which are which are used in the industries and the research institutes right now, like QGIS. Many of you are very familiar with it. Then GraphGIS, Google Earth Engine, Leaflet. We use Leaflet in a Python as a Python pipeline, but mainly focus on Google Earth Engine. And I could show you we can create like end result which we can show it to the end users, and that can be used by the you can say by your client in a very efficient way. So next, everyone is familiar with Google Earth Engine, I guess, or if not, you can go and look for the courses online. It's a I would say very easy and very easy to learn platform for someone from geospatial background, but not a coding background. So personally, I like it. It's very easy for me because it has input, output, and also the map result. Like when I work on the Python pipeline, we don't see the map. We used to import other packages to see it, and it's very sometimes it's very inconvenient. So personally, I like this platform, and it's open source for all the researchers and institutes. Okay, so what I found, I've been to a few conferences, and what I've seen in my 4 years of experience, I've seen that we deal with the environmental problems. That is the first result. Like geospatial has GIS is a powerful tool which can solve almost most of the environmental problems, but we stop at algorithm. Like we create an algorithm, we publish it, we give it in a research paper, and that's all. We don't implement it, we don't give it to the users or the end users. We cannot create accessibility without any third tool. Like without the help from the third person or third party. Like for the accessibility part, like creating UI or creating a mobile application, we stop there because like I've seen in my community that people don't focus on that part, but that is the most important part. Like if you create some algorithm and you cannot show it to the end user, like suppose you are working for an agriculture problem and you are not giving it to the farmers, what is the use of that algorithm? So I believe that GUI can be helpful in that part, and even a simple like using a simple UI, you can create the algorithm and you can create a UI and you can give it to them and they can use it for their end results. So why just stop at algorithm and the solution when we can create accessibility using this tool? So now I'll show you like what I have done. So the first problem statement which I had in my experience was the air pollution in the North India side. So this was like what you're seeing right now, that was the algorithm created by us. So all the white parts which you are seeing, that those are the brick kilns, which are the major source of air pollution in the North India sites. As I said, like this is, we can say because of the academia in India, we cannot publish it unless and until we have like all the signatures of the higher authorities. So I could not show you the end results, and unfortunately, it is not still out yet. But yes, it was one of the best work because it could help in like for air pollution. It is like a major problem in North India, and this is one of the best algorithm I created. And it could also show when it is started and how it is affecting the environment. Then this is the second problem, which was the mining areas. The project was how the mining areas are expanded over the years, and fortunately the geospatial data which we have, it is available since 1972. So we have like around 50 years of data. So we can see the expansion, we can see its effect in the surrounding areas using this tool, and we can just create a UI and we can show it to the clients, like we can show it the policies makers. Okay, like this, the mine is expanding over the years, over the months, and they can create their policies based on it, or they can work on EIA reports based on it. So I think this was one of the good application of Google Earth Engine in geospatial field. Next is when I was working for forest department, so they have this tracker around the animals. This is another application I found very interesting in my experience. So I created this algorithm which can help to analyze their psychological behavior or their movement behavior, and it helps in saving the wildlife of India. So this I could publish it online because it was my own algorithm, and I would encourage like my friends in geospatial community that they create such algorithm and they publish it online. Even though they cannot create the end result, it could be used by the other your colleagues, your friends in geospatial community. So this is another example. This is one of the other examples. So you can see the points there, those are the fox movement in Ladakh. So we can see that they are moving only along the vegetation part. That was interesting because when we see over the 10 years past data, and we see that why a particular species is declining in one region, why their corridors are missing, why they are not connecting, why they are not moving from one region to another. I would say that if we can find out the solution, or we can find out the reason with the help of Google Earth Engine, or with the help of the data sets of geospatial data, and we can analyze those results, we can save them because they are the important part of the ecosystem. So this is another interesting experience. Next, we created a package, and when I was working in the BH lab, so we created the package and we posted it, and it was the linkage mapper project. It helped in maintaining for the ecosystem functioning, And this mapper project, this helps in maintaining the balance and the habitats. It prevents the overpopulation of certain species, which can lead to the negative impacts on the ecosystem. And similarly, I posted my algorithm on the online, which could be used by the geospatial community. So I encourage you all, if you are creating something interesting, just post it online so that the people could like leverage from it. Next, the fourth step of my second slide. So I said that how we can show it to the end users. So that's where web UI came. So this is the website which we created, like with iCarda. So we worked with the hydroclimatology application. It will take some time to load. This is the end result I'm talking about. Like, you create your UI and just post it on the as a link. You can embed it in the website, and it will show the result. You can also include your logo if you want to. So this is if you want to see. We work for the MENA region. So if you want to see the temperature or soil moisture precipitation over the years, you can just see it in the UI, and it could be used by the policymakers or by the farmers or their community, and they could it will help for them in their application. This we created hydroclimatology results. We created biophysical factors. I could just show you over here. These are the biophysical factors. We have elevations. All this data is freely available in Google Earth Engine, so you can just access it from there. You just have to write a code and you can get it for, like, suppose if you want to work on one district or one city. Initially what we do, we just download a tile, or we used, even though if we use the raw data which is not corrected, but in Google Earth Engine you have level 1 and level 2, so it is already corrected data and you can use it according to your application. So if you want to work on whole region, not just one city and one district, and you want to work on all the region altogether, you can just use it, and you can include whatever factors, whatever variables you want to include in that, and you can just show it to the client, and they can use it based on their, like, all I'm saying is you just don't stop at algorithm. You can create an application which will be helpful to Okay, I think my net is very slow. But yeah, we got the picture. Okay. This is another example. We created yield and yield gap distribution. So this I did for iCarda. We do crop classification, and we have a potential yield based on some regression models, and then we have yield which is realized from here, this data, and then we created a yield gap which is helpful. Even the same thing which this I'm using right now in my current company also for agriculture trading. We're using the same thing, and we are using this data to forecast the yield of a particular crop. Say if you're working in oilseeds or if you're working in wheat, so you can forecast using this data, and it is pretty helpful because we are having around 10-meter resolution, and for agriculture field that is a good result. So this is another application. Then we created weather forecast tool which could help in forecasting. We have GFS data in Google Earth Engine that can forecast up to 15 days. So we used those tools and we created a UI which can help in forecast precipitation, temperature, wind direction, wind speeds, all those things. It is helpful for the farmers so that they can, suppose if, like right now it is not raining over here in India, so they cannot sow the consecutive seeds right now, which is used, which could be useful like cotton or other seeds. So based on this forecast, they can timely sow their seeds and they can get a good harvesting result. So we provided this tool to the MENA regions and also to West Bengal farmers community. Then this is another very surprising experience. Like I didn't know that we can use this geospatial analysis for the trading. So I currently am working for LDC, which is a trading company, and they trade in different commodities. Like you can see here, they're trading coffee, pulses, rice, sugar. I'm not allowed to tell the algorithms, but I could tell you like they use geospatial data to forecast the results of these agriculture commodities, and it's a pretty strong accuracy. I have a hands-on experience session, so if anyone wants, they can do it, or I will provide the link of this page, and you can just see there are 6 steps. I know most of you are coders here, so you can just create the same algorithm using in Python using backend and front-end technology, but for my geospatial friends who are not from the coding background, just like me, they can use this and they can create a UI which could be provided to their end users. So first we have data. It's very simple. Like you just need to include the data which you want to use. Like over here, I'm using Landsat data. So just put the Landsat data, put a AOI in which area. Like suppose if you want to work on Karnataka or a district of Karnataka, just put that and mask out the cloud results. So this is one of the function. It is already available on Google Earth Engine. So just mask out this function. And second is the component. Say you want a UI with a map panel and then intro panel and a little slider of the year, so you can just check the time series of that area. So you can create something like this. You can provide a control panel, a map panel. All this UI API, like it is available on Earth Engine. Yep. So as I said over here, we have a control panel and a map panel. Map panel to display a map result, control panel to show your print result, mainly a chart or any other data like area or something you want to display. Then you can define that based on the style and layout. You can use your artistic skill to style that that particular panel. Then you can include a map panel. We have satellite, hybrid, and a simple transit map. You can give a bit introduction. So this all the panels you want to include, and just combine them in one line. Like over here, you can combine them in one line. And if you want to use the default route, you can do that. Otherwise, clear the route and include your own panel. So in my case, I generally clear the routes because I want to define my own style. So I add control panel and the map panel and intro and year panel. Then for styling, okay, so for this it's just a styling like where you want what, and you can do it after creating a dummy UI, and you can style it as you want. Then this is behavior. Behavior is where you will add your algorithm. Like over here, I'm doing year change of a river. So I have provided the algorithm which will show me the year change for 2014. So I'm using the same data, but I'm changing the year and taking a mean of that data. Similarly, I'm doing it for every other years. This is the part where you provide an algorithm. Any algorithm, just connect it with your composition part. Then initialize it, because if you're not initializing it, it will not show the first result and it might throw an error. So this is the app link. Your UI will look something like this, as I said over here. A map panel, control, year slider, intro. So something like this. With those codes, you can simply create a simple UI, and you can embed that link to your website or your mobile app. It will show on. I even worked on the mobile app, so it does show on mobile app, and it will it's compatible with mobile application. This is the code. If you run the code, you can see your result in the map section. So whatever will display in your map section, that will be your UI result. And all those things, like all these APIs, they are available in the docs section. So you can just go through it. They have limited number, but it's sufficient. Like in this case, you have UI, so you can of map, and then we have UI of button. You can add a button if you want, or a chart you want. Date slider. I will show you one application for the date slider, and you can add a text box. Like if you want to say that over here the potential yield is this much, so you can use a text box for this. You can split your map panel into two parts and then use that in your application. I will provide this link. If anyone wants to go through it, they can Then this is another application. I just created a simple UI for the flood which occurs last year. So if anyone wants to analyze the data, and I submitted that UI link to the geospatial community, so it's in open source. I think I have it open, yes. So I've used date slider over here. If you want, you can change the date. It will take a lot of time, so right now I will not do that. And I've linked all the maps, so if you are moving on one side, you can zoom in on the other sides. And if you want to see what's the flood ratio or the area which is affected due to flood for 2 months or 3 months, you can just change the date, and you can use that as a number. You can use or to use as a text box over here, or you can just use your imagination, whatever you want to use, add as a panel, you can do that. So we can see over here, let's say it was not the good year for Pakistan, but this was really bad. Like we can see over here, the build-up index tell you about the urban area. So urban area decreased a lot in this part. You can do it district-wise. You can have a button for district, and you can just visualize it district-wise. You can see the area affected district-wise. You can have the number. Okay. Next. Yeah. I like this slide. Like people don't realize, but we have literally 50 years of data, and it is one of geospatial data. I think it is one of the vastly data, and it will be continuous. it's continuous data, and we have like so much of data, and we are not utilizing it, and even if we are utilizing it, we are not giving it to the end users. So I will motivate my friends in the geospatial community that they do that. They provide the end results to the users who can use it in a correct way. That's all for my presentation. These are some of the research institutes that use Google Earth Engine in India. There may be others, but these are the ones I'm familiar with. That's all. Thank you. Any questions?
So is there a way, when you show that UI, is there a way to go to the code from the UI itself? So suppose you have written, you can't see the code that is written.
No. Because you have a link like over here.
For authors, journalists to add a link in the app.
That way your algorithm is protected also, no? No one can use the algorithm. If you want to show it, like I've shown this thing. We add it on the website. No one can see the algorithm behind it. They can use the result, but they cannot see the algorithm behind it. So that way the algorithm is yours, but you can present the result.
Any more questions?
For your studies on animal tracking, what was it like working with the forest department? Is it easy enough to get their data and work with them, or how does it generally work?
They do, like for animal tracking, they themselves. I've worked with Wildlife Institute of India, so they go on the field, they do that collar tracking, and they collect the data. So what I've shown, that was 2 years of data, and I collected the NDVI for. Suppose it collects every 30 minutes or 1 hour, that depends on your tracker. So suppose it is collecting for every 1 hour, so at that particular time what is the NDVI of that particular region. So for that I've created the zonal statistic code, and then they use it in their own algorithm, and they analyze their behavior or their movements. Yes.
So you spoke about agricultural commodity trading, which is a very interesting application now in the commercial space because geospatial data is very underutilized.
Yeah.
In commodity trading, think of, you said agriculture, so if you think of avocados, right, as one commodity, you need multiple data streams. So you need weather prediction models, you need soil water prediction, energy as well, and then there is production, shipment, warehousing. In the processing models that you have, how many data streams do you use? What is the percentage of data stream influence in the sense that does weather overpowered, let's say, soil production? Or what is the percentage of how many data streams are going in? And does one processing model do that? And you go end to end, which is production, shipping, warehousing, everything?
There is no one processing model. Like I cannot reveal how we work, but we have different teams. So for weather, we have different teams. For research, like crop research, we have different teams. I'm working on that crop research. Then we have different teams for shipment. They do their part, but everything is related. So.
Yeah, so in the relation, can you tell us about the percentage of how much is going into that end product for the...
I cannot tell you that because I have experience with LDC. I mean, this was first time I'm also seeing that we are using it for commodities trading, and I cannot tell like how they do that, but I can tell you like they use GIS as one of the part of that whole process.
So a follow-up to that is, so there's one is trading, and then there's some companies now that use this trading data to also bet on stocks and other commercial value. Does LDC get into that as well?
No. We do our own trading. Like we don't give our data to someone else.
What is commodity trading?
That's a good.
So you have done stocks trading, right?
Okay.
So it is just like that. So you have to see where, instead of stocks, you have to see for sugar. I think we can talk about it later.
Yeah, those things we can have as a friendly chat, not in the camera. Okay, any more questions related to Google?
How versatile Google Earth Engine is in comparison with planetary computer?
Sorry?
How much versatile is Google Earth Engine is in comparison to the other platforms like planetary computer and open data registry of AWS using Why Skype?
Frankly speaking, like other than GIS, QGIS, I haven't used Planetary and those platforms, but this is open source for research industries. Like if I'm working in a commercial company, I'm giving some money to the
Google Earth is not just for production.
we are using it for analysis and we are using it to.
But it has a lot of limitation.
Yeah, I
Computation.
think both has some, I don't know, it's again like in Planetary is quite new, so you don't have good community support. It requires some issues. So that is what Google can do, but I think both has
And also Planetary computer is not yet mature as Google Earth Engine. We are just in the nascent stage of like building it.
No, like it has matured, like it has reached beyond Google Earth.
Oh, so I have experiences.
It is not much popular.
Okay, I have experiences like logging into Planetary and the server is like not working, but I don't have experience like that in Google Earth Engine. So I think it's a good competitor for Earth Engine, but still you have to wait and see how it is like turning out or unfolding.
I think both are not open source.
I will try that Planetary and then I will tell you the comparison.
That's what quite sometimes in the laws and like same what Google did. Now Google is like you have to pay money for services. For services,
Yeah, there you have to pay for if you want to use GPS platform.
Yeah, next question. Next question.
Yeah, any more questions to some related to Google Earth Engine, SAR, or even in data science, geospatial data science, is data scientist?
So I mentioned, so you mentioned one thing about providing the data to the farmers. So what method do you go through that? Like, are there ways in which the actual end farmers are able to access something like this, or does it go through a middleman?
So when I was working with the West Bengal project with ICARA, so we created a mobile app and we embedded these links to those mobile apps so they can. There were other features other than this analysis. There were other features like they can put their fields and everything. But this is also one of the features with which they can analyze their own field.
And then, sorry, just to follow up, so then is there a like a training or something that happens for those end users? How do they understand how to use this data?
So you're saying, yeah, training is there.
Okay.
Training is there. So there is their own community. We are not connected to each and every farmers. We are connected to the community of those farmers. So we provide to them the data and then they distribute it. And surprisingly, they all know how to use like mobile application right now. So that is the most beneficial part for us.
Okay, so further questions you will have it during the chai break.
Thank you.
Thank you. I'd like to thank Samyuta for her presentation on Veracity and Google Earth Engine. She rightly spotted the other powerful feature of Google Earth Engine, that is Google Earth Engine apps. So on our previous Let's Talk Spatial event itself, we talked about the analytical capabilities of Google Earth Engine, but she rightly pointed the Earth Engine apps, which are also a very powerful unit of Earth Engine. Here we don't need any hosting space. The Google itself giving the free hosting space to host that app. So I encourage everyone to go and try for it. Okay. Then now we will go for a short introduction section for everyone. What we will do is just let's start from the end, and you guys like introduce like who are you, what's your background, name, company you're working on. So we'll just have an introduction, and then we'll proceed on for the next presentation. Okay. Start from the back.
My name is Jared. I'm a MTech graduate in Geoinformatics. Currently working in ADO company as a GIS analyst. I want to pursue my career mainly remote sensing part, but currently I'm working as in the GIS part.
So, hello everyone, my name is Uday Rahman. So, I am working as remote sensing data analyst at Captain.
I am Cloud. I work in circuit analytics. I take care of the same data circuit.
Hi guys, my name is Gautam. I'm working at Spatial. So we are basically an edge computing platform, like where we can deploy models to the edge and generate analytics directly from the space. So I'm working as a part of Congress office over there. So I come from I'm not a hardcore geospatial guy, but I have a slight background of working with drones and GIS.
everyone, I'm Sagarika. I'll be graduating in a month. I spent my final year at ISRO working on remote sensing and processing models. I'm really interested in the business information side of geospatial data.
Hello everyone, I'm Ramya. I'm a product manager with a non-profit humanitarian open space company. Personally, I'm involved with the OpenStreetMap project in the last 8 years. Everyone's interested in learning about it.
Hi everyone, I'm Amit Chavda and I'm working as hydraulic modeler in Icons.
Hi everyone, my name is Aman. I work at Blue Sky Analytics as data scientist. I'm one of the co-organizers of this meetup.
I'm Anjnelu. I'm a data scientist at Reliance Geo. I work for the computer vision team. I was the part of the IPL team which hosted Geo.
Hi everyone, I'm Sajid. I'm working in GSPOC as a data scientist, previously worked in ISRO. So having worked there, I have got very much experience in like LiDAR, hyperspectral, multispectral and GIS data. So it's really nice to meet you all guys. Thank you.
Hello, my name is Pushkar. My background is in planetary science, mostly research on atmospheric and climate science stuff. I work at a Japanese company called Sonapne as a researcher, new to GIS, so glad to meet you.
Hey, hi everyone. I'm a product manager in Inside Planning. I do mapping more as a hobby, but I'm interested a lot in moving into this space. So I do a lot of work with OpenStreetMap and a lot of mapping. So nice to meet you all.
Hi everyone, I'm Janardhan. I'm working as a remote sensing analyst in Spatial. Hello everybody, I'm Gopal Krishna. I'm a tech student at NIT. Currently, I'm an intern at Spatial Analytics.
Hello everyone, my name is Manish. I work at Spatial Analytics as a remote sensing. Hello everyone, I am Rahul. I'm pursuing second year tech student in NIT and currently GIS intern in Spatial Analytics.
Hello everyone, I am Suraju. I am working in Spatial Analytics as a remote sensing.
Hello everyone, it's Sajjad. I used to work at
So, hi everyone, I'm Azam and I work at GalaxEye Space as a computer vision infrastructure. Hey guys, I'm Prakhar and I'm product manager in Galaxy.
Hello everyone, this is Rebecca. I also work at GalaxEye Space and working with I'm at GalaxEye, in my second year at IIT Bombay Hello everyone, this is Annie. I work as a geospatial analyst at GalaxEye Space.
You guys want to?
So, my name is Arya. I work as a full stack engineer at GalaxEye.
Hi everyone, my name is Ramcharan. I work at GalaxEye in the business development team.
Hello, it's Gopal. I'm working here as a process engineer in GalaxEye.
Hi, I'm Ayeshri. I'm also part of the business.
Thank you. We will have an introduction later. She's having a presentation. Okay, so I am Santosh. I work in Blue Sky Analytics. I'm a data scientist where we are doing climate tracking mostly. We are in a business-to-business company. We do like climate science data. And Aman is my colleague. Like I'm working there for like 1 year. Okay, so I just want to introduce our website again. So this is Let's Talk Spatial. We will upload all the presentations from our speakers to our GitHub, and there is a contact section in our website. Once you go in there, there is a link for Let's Talk Spatial Slack group. If you are interested, join our Slack group. There is section for internship, there is section for resources and other technical documents which we can share, and there is a general discussion. So as in geospatial folks, this is a general group to like be in and like hang out. If anyone is asking help, you can go and address it. If you need a help, you can come and ask for help. So if you are free, you can come and join this group. And we also have an GitHub space, Let's Talk Spatial GitHub, where we will upload all the presentations and our future event venues and everything. You can follow it. Okay, and also I just want to let you know the next future events, we need speakers. So if you are interested in like giving a short presentation like how we are doing now, you may not be an expert in a particular field, but you'll be working as an intern or an undergrad student, but you want to like share it with others. You are feel free to like come and approach us. That is one thing. And the next thing, like if you are happy to host us in your company, do approach us. Like we are on your mercy, like to host at different companies. So anyone interested, do approach us. Okay, so that's it from Let's Talk Spatial. Let's move on to the second presentation from Akshay Patel. So Akshay Patel is electronics and telecommunication engineer, completed his masters in radar remote sensing with focus on HPLA radar signal processing for ionosphere applications and meteor fragmentations. Then he continued working on a couple of DRDO and DST projects at IIT Bombay and completed his PhD from IITB Monash in microwave remote sensing with a focus on SAR data analytics for various applications. He have a particular interest in Earth observation satellites and ground radar image processing. Currently he is working with AA- as a remote sensing data scientist. He have worked on range of applications which were solvable using the optical radar geospatial data layers and OT.
Putting right? Correct.
Can you just check?
Yeah, test. Audible?
Can you just put it on?
Am I audible now?
Should be the other side.
That's okay.
That's okay.
Yes, whether it's fine.
Yeah. Am I audible now?
Yeah.
Hello all. So I'll be presenting today mostly around the SAR. So I'll be focusing on basics of SAR and then gradually move towards the application part. So the main focus of this presentation is that understanding the SAR information. So I'll briefly touch upon few technical terms, what do they mean, and if we understand those well, it is very easy to implement or analyze the targets. So I'll be covering the first part of the presentation would be mostly on the basics of SAR, so that particular piece will help you in analyzing any application. Okay, I don't want to jump to directly application part, because even if I explain you that, you won't be in a position to understand it. So let's talk about first the images, SAR images. It so often happens that we take an image, and if we don't understand it, we just say that it's of bad quality and we just throw it away. We don't actually acknowledge the engineering stuff that goes behind capturing those images, and that's the whole point of this presentation. You appreciate the remote sensing data. It's very difficult to capture. The engineering part is very tough. And once we get those images, we have to do the justice to that particular image. I have seen particular labs, they are working on single data set, but they are doing a very tremendous job. They are extracting every piece of information from that one image. So let's start this presentation with the basics. I'll just focus on the SAR resolution. What is the geometry of SAR capture? It's different from how optical image is captured. Then technical terms like wavelength, polarization, incidence angle, distortions that we get in the image, and speckle. And then I'll gradually move towards what is the frequency that we can use for a particular application. Not every frequency is targeted to particular application, so we have to select a particular frequency, wavelength, and polarization to solve the problem. And then I'll briefly touch upon how this R wavelength interacts with the target. And then on this entire discussion, I'll show a few case studies on agricultural domain. Okay, so consider that, so this is the flight direction. Okay, so it's at above Earth's surface 600 or 700 kilometers from the Earth's surface, and this is image footprint. And the geometry of image capture is different from optical. So optical sensor usually looks just below the sensor, not the direction. Okay, so this is a platform, and this is how the optical sensor works. But SAR works in side-looking geometry. Most of the SAR sensors are towards right-looking. You can develop the sensor with left-looking, but it is agreement of the community or whoever is developing the sensor. Mostly they are developing the sensor which is looking in the right direction. Now there will be a basic question, why the SAR needs to look at a target inside geometry and not at the nadir location? Because optical capture is different from SAR. It is radio detection and ranging. So when you capture an image, you want to project that on the image plane. And the differentiator in radar or SAR is the distance. If you capture an image in the nadir, for image, this instance and this instance is same, and both will be projected at the same location in the map. So you cannot simply do that. That's the reason why we are working with side-looking geometry. So this is a side-looking geometry. Okay, this is a near range, this is a far range, incidence angle. So these are some terms that are very essential when you actually capture the data. And on top of that, you build the modeling or understand the images. So wavelength is one factor. Slant range is nothing but this distance. Ground range is when you project this distance on the ground, that is ground range. Azimuth is along this axis, along the direction of the sensor. And radar, the wavelength, like typical wavelengths of the radars fall in higher wavelength as compared to optical. So that is the basic difference between the radar and optical sensor. Okay, so I'll just show you the animation of how exactly the image is captured with the SAR sensor. So let's say this is a path of satellite. It's going in this direction, and this is how the image plane looks. So this end is near range, this end is far range. Okay, and the pixel, what you see here, are not equal. The X resolution is different from Y resolution, and it so happens that a pixel size also varies along this geometry because it is side looking. So all sort of information is very essential, and it is different from optical. So this is an image plane, this is the pixel, and when we see the dimension of that pixel, this direction and this dimension is different. So this is called as range resolution, which is a function of pulse length. So it is directly proportional to pulse length. So if the pulse length is small, the range resolution would be more. That means bandwidth should be more. And the azimuth resolution, which is nothing but L by 2, that is antenna length by 2. Now this antenna by length by 2, it is there because this is synthetic aperture radar. This is a technique. If you work on real aperture radars, this equation is not there. That is the whole point of going to SAR. That means you want to keep the azimuth resolution as fine as possible. If you go with the traditional method of radar, to achieve this resolution in centimeter scale, the antenna length should be in the range of kilometers, 10 kilometers or 7 kilometers. You cannot deploy that in a space. And that's why we are using synthetic aperture radar technique here, to synthesize the virtual antenna from small size antenna. And that's how we are getting the benefit here. That means the azimuth resolution now is directly proportional to length of antenna, physical antenna. So right now it's advantage. You have to reduce the antenna to get better resolution. On the real aperture, it's completely different. You have to maximize the antenna length. So this is the old equation. It is directly proportional to lambda, inversely proportional to antenna length. So to achieve high resolution, L is now in the denominator. So that's the whole point of going from real aperture to synthetic aperture. So this is the mathematics. I already explained you that. So this is physical antenna. Okay, and if you use this theory, lambda by d, it is the dimension of the. But as you see that, you can replace it with this distance, that is beam width. So it's completely, I would say, signal processing task. There is a Doppler shift involved. There is a matching filter. So it's a huge signal processing task to synthesize the virtual antenna from physical antenna. So it's a pictorial representation. So you know about the Doppler shift. When the target is moving toward the source, you get a positive shift. Away from the source, you get a negative shift. So as the plane, or let's say there is a payload on the plane. If plane is approaching the target, you get a positive shift. Here you get a zero shift. Here you get a negative shift. So these are individual returns. But with signal processing and all sort of off-board exercise, you collect entire signal from the satellite and you downlink it, and then you do the processing to increase the azimuth resolution. So you can see that the satellite is moving from point A to D. There will be individual return at A, B, C and D. Then you club them and synthesize your aperture. So if you see, if the satellite is moving from point A to D, so within a duration t with the velocity of v, what is the aperture that we can synthesize? It's t multiplied by v. So actually we are synthesizing the antenna length in the range of kilometers with only small antenna. That is the value addition of SAR, and that's why it's so popular. This technique is not specifically used in SAR, but it's a derived one. It has been used by other application, but synthetic aperture radar is the most popular technique where it is happening at a very large scale. Okay, so when the sensor captures the image, whatever data that we receive is in the slant range. Okay, always consider that the radar or the SAR sensor is the projection, orthogonal projection. It is not what we see in the ground. All the objects when we see from the side looking geometry, they are compressed. So the building length will be compressed. Even though if it is a square, you will see the rectangle because of this projection. So this is the square target, but when you project, this length gets short. So whenever we receive the image, we have to convert it from slant range to ground range. And for that, you require all other parameters like height of the antenna, the satellite parameters and all. So this is one of the example. This is what the image looks in the slant range. This is how it looks in ground range. This is a true picture of a SAR, and this is slant range geometry. And now we are seeing here the color image. But SAR, when you see, this is the composite image. So you get the HH return from SAR signal, VV return from the SAR signal, or VH return. Then when you push those channels into RGB, you end up getting this sort of picture. Now what you are seeing here, you are seeing different colors of crop area, like croplands. Okay, so if you know what HS represents, what VV represents, and what VH represent, what is the physical significance behind each component, and when you try to push that into RGB channel, you get a sense out of it what the target is. Let's say I know the relative distribution between HH, VV and VH is almost same for one target. Let's say it's X, X, X. When I do the composition, I end up getting a white color. So I already know that this is possible for a target, particular target. Then I can classify that on the image. Now this is a very simple way of explaining it. You can then fuse this with data science, signal processing and everything. You can do it at a scale. So the SAR operates in this range, like X band relative. I'm just showing it with respect to human dimension. So X, shortest wavelength, followed by C, L, and then P band. So 3 centimeter, 5 centimeter, 24 centimeter, and somewhere close to 30 centimeter. P band is close to 30 centimeter. Okay, so this is how the SAR signal operates. We have right now X-band sensors, TerraSAR X, PAS, Cosmos SkyMed. We have C-band, very popular, Sentinel-1. Everyone knows it. This is the most popular satellite, most stable satellite. Okay, and it has a huge application. And L-band, we have only one L-band sensor in the world, which is developed by JAXA, ALOS Pulsar, ALOS 1, ALOS 2 series. And right now we are having NISAR sensor, which is NASA ISRO sensor, which is a dual frequency SAR, which is for, I think, the first time in the world that we will have a dual frequency signal on the space. It's S and L band. Now, one of the important factors when it comes to SAR is understanding the polarization. Now, what is mean by polarization? We know that the electromagnetic signal has E and H component. Both are perpendicular to each other and also perpendicular to the direction of the wave propagation. So, when wave is propagating in Z direction, the E component will be along X and H component will be along Y direction. This is how the scenario looks. Now here, for simplicity, when we convert it in a V and H component, we see that the point of E, the fluctuation of E vector is in vertical plane. Okay, it is vibrating like this or else like this. So this is very pure polarization that you can end up getting, HH and VV polarization. So this is V polarization, this is H polarization. So theoretically speaking, you can also take H polarization because those are complementary. If E is in H, you expect that your H is the magnetic component is Y direction. But it is agreed in the community that when you define the polarization, you stick with the E vector. Okay, and this is a very ideal scenario. In real life, you won't get this in natural domain. This is what instrument generates. This is how the SAR sends the signal. But when you want to capture electromagnetic waves, it is in an elliptical polarization, the most general form of the polarization, this one. Okay, so this is elliptical polarization wave. Most of the time you will end up getting this, any deviation with this. If you make your E component, X and Y component of same size, you will end up getting circular polarization. And then you just have to quiz this in one of the direction. You quiz this like this, you will end up getting the linear polarization. So with this, if you have equation for elliptical polarization, you can synthesize any polarization, and that's the whole point. So that's the whole point. Most of the SAR sensor works with HH and VV. That is a full polarization information. Okay, when you send H signal, you receive H and V. That means you have two components, HH and HV. Then in the next cycle, you send V, you receive V and V. H, you have VH and VV. So the full polarimetric SAR gives you all the information regarding the target polarization. That is the complete picture. See, the Sentinel-1 is dual band, so you will not get the complete picture. Most of the sensors which are commercially available right now, those are single pole or dual pole, because full polarization at scale, operating at every time, okay, capturing entire, is not feasible at the moment. The payload size increases, the processing increases, thermal noise increases, instability increases. There are high failure chance if you run the sensor whole the time, the duty cycle of the satellite. So the off period should be very high than on period for the huge assembly. On the Sentinel-1 is like dual pole sensors can do that trade-off, that I will capture the data only one polarization, but I'll give you the data 24/7. So that's the trade-off that we have to do. Okay, this is I already explained. You send the H, receive V, and all the other combinations. So you end up getting HH, VV, VH, and HV. Okay. Now HH and VV, HV and VH ideally are the same when you see on the image, because we are working in backscattering geometry. Okay, SAR is backscattering geometry. You send the signal, you wait for signal to return in the backward direction. Okay, there is always some forward scattering in the SAR, but you are not able to capture that because there is no other sensor capturing that information at that end. So it's always backscattering. Okay, now I'll just touch on the incidence angle. What's the incidence angle is, and how is it impacts the signal of SAR. Okay, so as I explained you, SAR works in a backward geometry. So consider this is a surface, earth surface, this table is earth surface. If I take a ball, okay, this is very smooth surface. If I throw it at this angle, 45 degree, I expect that my ball should go in forward direction. That means entire energy is going in a forward direction. I am not able to receive any backscatter. Now why this is happening? This is happening because this surface is very smooth. Okay, there is no undulation, and that's why it acts like the mirror and the ball goes in the forward direction. On the other hand, let's talk about that I introduce some sort of undulation in this surface. Let's say zigzag pattern. No matter at what angle I throw it, I have some probability of getting that signal in backward. Correct? At whatever angle I do that. So I receive some backscattering. So that's the idea of understanding what's going on the ground. If you know this, like incidence angle, wavelength, then you are able to characterize the target. With this two observation, now I'm in a better position to say, hey, for this image, if I'm seeing this scenario, there might be the smoother surface there. And if I'm looking at this, there might be a rougher surface. Now, how incidence angle is making sense here? So if you see this chart, okay, as I already shown you, if this scattering, this smooth plane scattering is very sensitive to incidence angle. If I keep my incidence angle very close to nadir in this, I have a probability of getting it in backward. Okay, but this sensitivity of entire with respect to theta, sensitivity of return with respect to theta is very high. Even if I do the minute change in incidence angle, my backscatter drastically changes. That's why the rate of change is very steep here. Okay. On the other hand, if I take my surface which is undulating, the sensitivity with respect to incidence angle is very low. No matter what my incidence angle, if I change it from 10 to 12, the backscattering won't change that much because I'm expecting some return signal backward direction. So this is how you can characterize a target. Okay, now I spoke about the incidence angle, considering the surface is flat, but naturally it is undulating, and that's why at each point we have a local incidence angle. Correct? Even though satellite is throwing energy at particular angle, the angle will change with respect to undulations. So it is a high incidence, local incidence angle, short local incidence angle. So what you can do, how you can do is, the steeper slope have local incidence angle, low local incidence angle. So there we require the digital elevation model to compute the local incidence angle. So let's say you have a SAR and in the metadata you have a local incidence angle. Now I ask you to compute the local incidence angle. What input do you require? It's digital elevation. And from that you can derive the local incidence angle. Almost whatever modeling you do, like parameter estimation or let's say time series analysis, you end up working with local incidence angle. You never work with incidence angle, because what is incidence angle? From this point, that is near range to far range, it is constant, correct? 10, 20, 30, 40, 50, like that. So it's a constant shift in green. There is no information if you just see that. You have to match it with DM, and then you can see the features which are sensitive to incidence angle also. Okay, the picture gets more clear when you have the real image. So we have here the SAR image, correct? And we have the rough surface, we have water body, which acts as a smooth surface like table. Okay, what I told you is that for smoother surface, the change of backscatter is more with respect to change in incidence angle. So as the incidence angle is changing from this to this, you can see the shift in the brightness, correct? At shorter wavelength, I expect high backscattering incidence angle. So here I get a bright spot. As I move from this direction, target is same. It is water, but it's behaving differently. If someone who don't know the incidence angle theory, you will end up getting you will classify this object as a different, correct? So, but here if you see, this is a rough surface, there is homogeneous tint to brightness. So that's the importance of incidence angle. Another way, like as soon as you, has anybody saw here this R image, Sentinel-1? Please raise your hand. I think most of you have seen Sentinel-1. Any other sensor? Radar sat, see, Canada, okay. So there are many distortions in the SAR that we need to first filter out, or else we will end up getting bad results, or whatever algorithm you are developing. If you don't remove those, then you will end up getting the wrong predictions. So consider this scenario. As I told you, its slant range geometry has to be projected in a ground range, correct? Now consider this is a hill with like slope is not that steeper. Okay, the top point, if you see, if I project, the SAR signal comes here, I have to project this here, okay? Then the bottom, I am projecting here. So this A point is projected here A, this B point is projected here B. So this length is, in actual it's large, but on projection I am getting a small. So what I am getting, this distortion is called as layover. Now as I change this slope, the layover gets prominent, okay, like this. Shadow is going to be there, okay, it's understood, shadow is going to be there. If sensor is cannot see after that, shadow will be there. Let's suppose the extreme case of layover, what you can expect is that the slope is so steeper that the top point falls here and the bottom points come here. So it's completely flipped on the project plane. So point A, which should be here A, it ends up getting here. So it's completely flip over. So that we have to compute. And here the local incidence angle comes in the picture. There are some specific conditions. It's very easy to code. It is not something very difficult. You just require, you have to compare it with some reference theta. If theta is greater than this, do this. If theta is equal to this, do this. And that's how you can just mask the shadow and layover. We have inbuilt function for this in Snap application portal, Sentinel application portal. Other important factor is noise in SAR. So we are seeing that the SAR is coherent. When we say it's a coherent scattering, that means you do the vector addition. In terms of SAR, whatever target you are seeing, we assume it is a distributed target. That means we cannot definitely say that, okay, hey, this pixel is completely from the building. We expect a distributed target. So whatever signal we are getting is in the resolution set, correct? Let's say this SAR resolution is 3 cm. We are capturing the information in the 3 cm grid. And whatever returns we are getting are basically vector summation of each individual return. So when you do that, you have a high probability of changing the backscattering pixel to pixel so randomly. So it appears as a noise, salt and pepper noise. Okay, like this. Even the target is same. Okay, it's building only. But due to this coherent scattering, you end up getting noisy signal. That is called as speaker. You have to remove the speaker. Okay, there are different techniques to it. So one thing is that the raw image of SAR, which comes with speckle noise, has the highest possible resolution. But while attempting, like if you attempt to remove this speckle noise, your resolution goes down because you have to do the averaging, either time series averaging or spatial averaging to counter this speckle, and you end up getting poorer resolution. So even if you have a 3 cm sensor, the useful product that comes out of it might be at 6 meter, because this noise is so prominent that you have to reduce it. Without reducing that, you won't get any information. Okay, so it's simple like that. So you have phase shift with constant amplitude, then you will get some reduced scatter. If you say the phase shift is 90, there is complete off between the two waves. That means this peak and this gets cancelled out. You get a very low return. and then intermediate return. So it's constant jumping between bright and high returns. There are speckle separation techniques. There are standard libraries to it. Okay, so there is some Python script also where you can just throw the image, give the kernel size, and you can get the speckle filtered output. There are some intelligent way of doing it, and there are some very basic that anyone can implement. You just take the window, averaging window, move it, the speckle will get reduced. But that window is not intelligent enough. It will not consider that, hey, this is a water, this is the urban area, I should adapt to that particular region. So those filters are called as adaptive filters. They take into consideration the local statistics of the target. So there are many filters, and trust me, even if you implement all their filters, you will not be in a position to say which filter is best. It's always a case dependent. If it is serving your purpose, use that. So there are papers comparing this filter performance with different techniques, but you cannot surely say that for agriculture this will work. You have to keep trying. And even if you can invent your own filter also. So this is the raw image, how it looks, black and white, but with noise, too much noise. You apply the speckle, you get smoother. But there are some artifacts, those will be always there. You see there are some distortions in the image, that might not be true, but that are introduced in the speckle filtering process. So your whole point is to get the true picture with the whatever techniques you use. Okay, there are multiple techniques to it. Now how to select the SAR wavelength for your application. For SAR it's all relative. So when you want your target to be responding to your wavelength, correct, the size should be comparable. If let's say wavelength is 3 centimeter and your object in the scale of 500 meters, you will not get any information from that. The target size should be less than or equal to your frequency. So if let's say you are working on a crop and you just want to work on the leaf, the top area where the leaf size are 3 centimeter or less than 3 centimeter, you will use the X band. But let's say you want to understand what's happening in the stem, okay, that is bigger than 3 centimeter. You will require L band sensor, longer wavelength, or C band sensor. So this is all relative, and there is no fixed wavelength to any application. It depends on the crop, it depends on the application. Soybean, if you are working on soybean, you will end up getting different, you have to work with different wavelength. Sugarcane, you have to work with different wavelength. So working on the C or L, that is high wavelength, what you can do is you can see through the canopy, you can see through the crops. You might have a probability of getting something from soil if you want to compute the soil moisture. So every application is specific to incidence angle, frequency, it's all relative. There is no definitive here. If you have one image, you will hardly do anything with it. If you have two images, okay, the chances of getting information is much more. Yeah, I already spoke about the roughness in a very simple manner. There are some mathematical ways of expressing these roughnesses. Let's say root mean square fluctuations of the surface with respect to normal surface. Then correlation length. Let's say if I want to characterize the smooth surface, okay, what is the characteristic of smooth surface? The undulations of the surface would be very small, okay, and if it is a continuous field, the correlation between this point A and B will be same at any other point C and D. The correlation length is very high. Okay, for rough surface, the RMS fluctuation would be high, and even the correlation length would be small. That means if I move from point A to B, the relation between these will change rapidly. These are all things that goes in the processing. These are some technical aspect that goes into modeling. It's like that only. I already explained you the table theories. If it is a smooth surface, I get a maximum return in the forward direction. If I have a medium surface, I have some probability of getting in back direction. The rougher surface, I get most of the return in backward direction. Okay, it's too mathematical. Okay. Anyways, I'll just explain. If let's say, don't get intrigued by this slide, but let's say your incidence angle is 30. You kept it constant. And you have 3 sensors, TerraSAR X, RadarSAR, Pulsar, X, C, L. So you have kept the frequency variable, lambda 1, lambda 2, lambda 3. Incidence angle is constant. So the scale, H, the undulation, for which it is sensitive, it's 0.45. So anything below 0.45 at 30 will look like smooth. So consider the same scenario but at 50 degree and see this table. Okay. Now consider TerraSAR X. This TerraSAR X, the value is 0.60 centimeter. Okay, 0.60 centimeter. Okay, what is this? Smooth. So anything below 0.6 undulation will look like smooth in the TerraSAR X. Rest all will look rough. Okay, so that's how the incidence angle and theta, incidence angle and lambda comes in. You change the frequency with the same incidence angle, now the roughness threshold is increased. Anything below this will look smoother, anything above this will look rougher. So this background has to be known when you want to work with SAR data. Okay, okay, I already talked about this slide, but just pictorial representation. You see the phenology of plant is changing, structure is changing, moisture is changing. SAR is very sensitive to structure. Keep in mind structure and moisture. By means of moisture, what I mean is the measurable quantity is dielectric constant. So these two factors are very important, and the agriculture domain actually offers that. The change in structure when the plant is going through the phases, also the change in moisture. So it's a very good use case for SAR. Okay, the same theory. You get a return from the top that can be characterized by surface or volume scattering. The second wave is going to the soil, that can be classified as a surface scattering. And when you get multiple returns, just random bounce back and go, that is a volume scattering. So these are different components. Okay, so some technical terms I won't go into that, but just keep in mind you have different layers of information when it comes to SAR. Okay, again the same, I won't go into this slide, already explained it. Yeah, how can you classify the different crops? Okay, as you know, every crop has different structure, moisture. You have to use that information and create something. So let's say you're creating the RGB picture out of it. So R is HH polarization, G is HV, and B is VB. If you have a ground truth, let's say you're going on the field, you know exactly what is the crop, what is the stage of growth, what is the moisture. Record it on your table with lat long. That is your label data set. Take a picture on the SAR sensor with these 3 polarization. Okay. Now you have a ground truth. You have this, you create a composite. You will get an idea, okay, the ground reality for corn is this, and am I getting magenta color. So anywhere I am looking here, wherever there is a magenta color, I expect that is corn. Okay, this is what a very simple way you can do it with one image. There are intelligent way to do it with data science or ML. So this is at scale. This is very specific to one case study, but at the end you want to generalize. And when you want to generalize something, the data that you work should be huge. It should capture all the conditions. If you train the model, that should be scalable. Okay, the model should not overfit. Okay, it happens that if you use very limited data, it's overfit and it understands the data itself. It will not reproduce the result anywhere else. Again, I have shown this scenario with RGB channel, same sensor, different polarization. Correct? Now you consider the RGB channel is receiving the information from multiple sensors, X, C, L, RGB. Then you create a composite. Again, the theory is same, the practice is same, just the information has changed. Another information would be capturing the soil moisture. So there is a standard algorithm available in SNAP, integral equation modeling, where you just have to provide it's very good practice. You can download the Sentinel-1 HH or HV image. You just throw the image to the black box, it will give you this soil moisture information. So at a time series, you have a moisture at D1, D2, D3. and you can actually see how the moisture is changing. That is one of the benefits of SAR. Tillage practices. Now, which property of SAR would you think help here for tillage practices? What theory of SAR, when you look at the tillage image, what we do first thing? Roughness.
What's tillage?
And smooth.
What's tillage? What is tillage?
See, it's like plowing technique. So after you have to prepare the farm for a new plant crop cycle. You have to dig the surface, okay? So to just that you shift the layers, okay? So you introduce the air pockets into it. Any worms or something gets exposed to sun, and then you get very dry soil like that. So actually you are increasing the roughness, and now your target is I want to detect the roughness. Okay, so it's indirect detection. Tillage is responsible for roughness. So whatever you see, white patches are where the tillage has occurred. Black, no change, and green. This is the green cover. Okay, that can be done with multiple ways. You can work with one SAR image, two SAR image, or very popular in SAR. You work with two sensor, SLC, phase information. You capture the distance change with respect to phase. I have not covered the inside here because I just wanted to make sure that the basic is well understood here. So the next part, if you go in deeper and deeper, the next part comes in SAR is polarimetry. So you understand this SAR, you go to polarimetry. Once you are done with the polarimetry, you are going to INSAR, then TOMO-SAR and all. These are advanced. One important thing when you take the SAR images, we always say that SAR is not affected by cloud or something it can see through. That is true. But when there are some extreme weather conditions, when there is a rain, we get a backscattering from the water. It's very sensitive to water. Water dielectric constant is 80. Okay? There is high attenuation in water. So whatever you are imaging, it will be completely get corrupted by the rain event. Even the dew, morning dews, that impacts the SAR backscattering on the plant. Okay? As we know, the water dielectric constant is 80, highest among any natural body. Okay? But let's say the water is frozen. The dielectric constant directly jumps from 80 to 3. So ice is 3.14, close to 3.14. Snow is between 1 and 2, 1 or 2, 3. That is based on the thawing cycle. Okay. So we know that SAR gets attenuated in water. Correct? But let's say scenario where the water is frozen. It looks dry to SAR. And then you will see that there is no water. But in fact there is a water which is frozen. So you have to know that also. So weather is very important factor. So you have to avoid images whenever you do the analysis. Go to meteorology, forecast of something, get the metadata, anything. If there is a rain event, avoid that image. Okay, with this I will close this presentation and we can open for question and answers.
Open to questions.
So, for Sentinel-1, what will be the best resolution?
Sorry?
Sentinel-1, what can be the best resolution I can use it, like, when considering, we know, like, it's multiple location, like, what resolution I should take?
That's completely depends on the application. Let's say, for example, there is a lot of interest in community for SAR. I'm seeing that many businesses are saying that, hey, that cannot be solved with optical. Can you do something with SAR? But you have to see what is the target. Let's say I have to work with utilities, vegetation management or anything in the urban area. Okay, urban area is too many objects and you will get a very random scattering from there. In fact, the background gets too noisy, you will not able to understand what my foreground is. So if you want to study the road, you cannot do that with SAR in this settings, urban settings. Okay, so it completely depends on the application. Whatever product I have developed, I have to do the processing and I reduce my resolution of all the, I worked with Terrasat, I worked with TerraSAR X, PAS, Cosmos SkyMate, Sentinel-1, all these sensors. whenever you want to show the results to client or let's say in front of community, you have to show the result which is multi-looked or speckle removed, and my resolution ends up getting 10 meters. So even my raw resolution is 3 meter or 2 meter, I end up getting 10 meter. So there is no and one important factor is that if you increase the resolution, you are increasing speckle noise. There will be too much random noise there. So I think there are some companies doing that with high resolution, but it's very difficult to handle all the things in the same sensor. That's what I would say.
So are these theories well studied, or space tech companies have to calibrate something, they have to work on top of it? Is that the value that they deliver, or they just integrate it?
No, first of all, when we launch the payload, then the agency has to calibrate it. Okay, without calibration, you cannot scale it.
So it's auto calibration model that they have to deploy, or they can
no, what they do is the sensor takes the image. Okay, we have some corner reflectors on the ground. You know, you place intentionally some objects, okay, well dispersed with well-known dimension. You know the dimension in X, Y, Z. You know the material, what the material is. You know the dielectric constant of it. Then based on that, you take that particular instrument in the lab, in the anechoic chamber, and you simulate the same situation that you are doing with a sensor. Let's say you are transmitting the power at X from the satellite. You transfer the same power in anechoic chamber, but right now you are now removing the atmosphere. 800 kilometers of atmosphere you have removed. So whatever response I am getting from this target will be different from real-time scenario, and that delta you have to calculate, and that is what it means by calibration. Okay, and those calibration constant comes with the metadata of image, of SAR image.
But that is different for different places. So how do you generalize?
That's why it's a very extensive process. Calibration is a very extensive process. So I'll just share a small story. We have a research satellite, correct? For Indian SAR satellite. There has been calibrations that is going for like every year there is a new study on that. Let's say A team has done some calibration, come up with this figure. B team is coming with this. Okay, and then we have to take into consideration entire data pool, and we have to release the calibration constant. It happens that most of the time, if it is not well calibrated, the calibration goes off. It's not uniform. It's a very important step that one has to do. So all the good sensors that you see, which are popular or which are like Sentinel-1 is the one, their calibration is too accurate because of they have even the continuous data. The community is used. ESA is in fact doing the large scale validation also. So the validation that we do, it should be done by community. It should not be done by agency. What I mean by that, in India, I studied my PhD in cryosphere. So I actually was working in Himalaya for understanding the snow and ice and all. So I have not got a very good quality ground truth anywhere in the Himalaya. That's the whole point. I have to go there, spending 30 days in the ice or snow, minus 13 degree in the DRDO lab, getting the measurements on the ground early morning 5 a.m., late night 8 p.m. I have to go there, collect the data so that I could validate the models. But as a person, I could do only a small area. Whatever it comes out of it is not generalizable. Correct? It might be too specific to that area. On the other hand, if you go and do the same study in Europe or USA, they have a snow portal, snow telemetry. What they do is, they have a sensor in the mountainous region. Okay, they capture the local information, they transfer it through telemetry. Okay, and then send that to the common location. It's a ground truthing only, but intelligent way of doing it. No manual intervention is needed. So actually it is the communication happens in the sporadic E layer, which is high electronics component layer. DEC is very high. Electronics layer, like if you can imagine it as a high electron density in the sky. It is one layer where you send the signal, it bounces back. Okay, so whatever telemetry happens there, through intelligent network. There are some portals where, let's say you are staying in Colorado, someone is staying in California, you have come in, the data set that government gets is from the community. I will go out of my house, I will measure the depth of snow, and I'll just record my lat long and just upload it. So these practices should be there so that you can actually develop very scalable.
So when you spoke about the mapping, right, you said there's a large area and then it's sort of an incidence angle into a smaller thing is what the SAR is capturing, right? But these are for stationary objects that you spoke about, crops and mountains and land.
Correct.
But shipping companies now are investing largely in SAR. But you see movement in ships. What kind of post-processing do you need to actually accurately tell those images?
That's a very good question actually. When we consider this, that we can do this synthesis of the antenna, we have that assumption that the target is stationary for a couple of seconds. If we do with that assumption, that is the whole point of synthesizing it. That means if I'm capturing the image at A point and moving to B point, my target should be stationary. There should be not any distortion with the target, so that I can club the information. Okay, but when you see the movement of ship, it can introduce artifacts in the image. I have seen it. So it can cause the positive Doppler shift, what I mentioned, relative shift. Okay, you get very bright plus sign scatter. So what happens is when there is a movement, actually the synthesis process, if you see the raw image, it is the bright spot of plus. Any intense scattering gets sprayed in the range direction and azimuth direction due to shift. And we have to minimize it with matching filter. Okay, so when you are synthesizing this in your local machine from taking the satellite data, it is taken care of. Okay, so the shift in Doppler due to this satellite, relative shift with the target, also the target can move for a very small acceptable limit. If it is within that range, that process takes care of it. If it is beyond that, I guess there are some other techniques which I think active R&D is going on that there.
Yeah, but it's mostly on the defense side, right? Because it also depends on the speed of the object that you're seeing and then what that filter is.
Yeah, correct. But most of these SAR applications, what we see right now are getting the attention in maritime applications. Sea study, CI study, ship tracking, oil spill detections, okay, regular movements on the port. So those are the very active applications of the SAR right now. So what happens is, when I give you the picture of Earth surface, the scattering is too random, difficult to understand. But when you have the calm, smooth water, so foreground, the background is very smooth. If you get a very intense scattering from foreground, it's actually picked up very well. So it's actually without any machine learning, if you apply some threshold, you might end up getting entire shift detection with just one threshold. That can be done.
Hello.
As you said that there has been a lot of interest in SAR imaging, but we know that SAR image is not dependent on weather and it is involved in light imaging. But what are the other main factors that make it so interesting?
Okay, so it's always the complementary information that you get from one sensor. As you move from one sensor to other, I'm not saying that this is the only sensor that you should work with. I worked with SAR, and the more time you invest in SAR, the more you know the limitations also. So if you are using optical, there are some drawbacks to it. Then you will move to SAR, then you will move to hyperspectral. That's why the industry is growing. We have now at every instance, every frequency length, we have different companies which are coming and delivering us the data. So there are some, if you go and see some interesting use cases of SAR, there are very exciting use cases. You can actually see the sea currents also. The water surface, the underneath sea currents up to some centimeter or meter based on the wavelength. So under sea motion also you can see. Wave capillary action you can see. So if the sea is very smooth, correct, and if you have capillary action, you can get a black scattering from that. So you can actually measure what is the distance between the waves that are forming along the coastal region. So there are very interesting use cases, but if you want to really see what is the potential, how the SAR is used that much, it's got attention, there are different applications. INSAR is a very important application. Most of the applications that we see with Sentinel-1 are revolve around INSAR. It can be, INSAR has a two product, the coherence map, the amplitude information and the phase information. The amplitude information can be used for particular application. The phase information can be used for particular application. Earthquakes, land deformation, change direction, encroachment. These are some of the use cases when you go with INSAR. The advanced INSAR, if you go into advanced stuff, correct, there comes the TomoSAR. So whatever you see with the CT scan in the lab, CT scan camera, the slice of brain or slice of body, you take a three-dimensional picture that can be simulated with SAR. So if you have multiple acquisition of the same target with some separation in the Z plane, you take the image from this axis, then you shift the altitude or offset it by some distance, you take another image, third image, fourth image, so you are separating actually the target in Z plane. As you shifting the center here, you are expected to get that 3D structure from the forest. And in fact, there are some studies where you see that there is a tomograph created by SAR signals. So entire 3D structure can be created for the forest. So, but the data availability, it is very controlled experiment. This is not something which is scalable now.
The telemetry samples that you get, I don't think it's a population, right? You have to estimate the population, right, for a system.
For which one?
The snow telemetry data and all. You get a sample of points, right?
For which?
The Himalayas and all you were saying.
Oh, yeah.
You take a sample, or even in the Western countries, it's a sample. You have to estimate the population. So are the current algorithms like centtelemetry and stuff like that, and are they able to satisfy those, or the R&D is really putting in efforts to?
No, it's like what I told you is that the ground collection. That means if my target is to estimate the ice depth, snow depth, what I'm going to do that there. I am measuring the depth. It's just in centimeter or meters. Okay, and then I have to forward it to a central pool. I get the data, and then that data is open. Okay, the researcher has the freedom to use that data. Okay, there might be some pre-processing, engineering, there might be some trend analysis. Okay, but that has to be done. That is independent. Okay, everyone can follow different techniques.
When it comes to optical or optical data, sensors across the sensors, we have seen standard formulas like NDVI.
Okay.
Across the sensors, it's the same. So it is generalized, and we can scale it to any area or any area. When it comes to SAR, it is different. So there will be more misclassifications. How do you deal with that, and how data science is helping in this area? And also when it comes to hyperspectral, so we have a particular unique signatures that can tell us this particular property is this and this. So we don't have any such information. So how do you do unsupervised classification, and how, because labeling all of the data is really a difficult task, and if you don't label it, obviously we get misclassification. So I'm not more into SAR, so I just wanted to understand what exactly is going on in present.
Yeah, I got your point. So you spoke about optical sensor. Okay, there will be multispectral. Okay, so multispectral sensor comes around 20 or 10 meter resolution. Okay, different bands at different resolution. So there has been established studies. Okay, for let's say NDVI index, NDWI, NDSI index, PSRI, VARI. There are many indexes. So we have to do the same study on different sensor. There are some index. Let's say there is a NDVI in optical. There is some other index which describes more closely, like correlates more closely with NDVI. Means what is the importance of NDVI? Characterizing the vegetation. Correct. So in SAR, in optical you have that band 1, band 2, band 3, so that you can do the index calculation. In SAR, what you have? You have VV, Let's say you have only two pole, HH and VV. So you do all sort of calculation with that, you come up with the index. Of course, the magnitude of indices is less when it comes to SAR, because we only have a maximum 4 measurables. Correct. When you are saying hyperspectral, we get a signature, smooth signature, because we are sampling at very narrow bands. So you get a complete picture, so that you can understand the target very well with the hyperspectral. The limitation there is data handling, data cube. Okay, so I'll tell you that I've seen 5 centimeter near map image, optical image, RGB image only. The one image, very small image, is 8 GB. It is not able to load in QGIS itself. So data handling is challenging in hyperspectral. When you consider about optical, you cannot connect the dots, multispectral. 8 bands you cannot form any wavelength. So there you have to rely on different techniques. Like you told that with the smaller samples, how can you do the well scalable modeling? Correct. You don't have always that advantage of collecting the good samples or a huge chunk of samples. I think there are some machine learning techniques. I think long shot, long shot, and then there are some techniques coming right now addressing the same issue, that with a smaller labeling data set, how you can scale the modeling. Okay, so there are this active learning frameworks now. So these are challenges, work are there, and I guess many good papers are coming nowadays. You have to incorporate them.
So my main question here is, if you select one particular sensor, let's say poles or whatever it is, so if you develop a index for that particular sensor, will it work the same with other sensors, or
no, you have to do the comparison study. It's all relative.
But when it comes to NDVI or something, it is always same with different sensors. So is there any generalized studies that is happening in this?
Yeah, there are some studies going on. Let's say I've seen that if you take the Landsat sensor, the NDVI stability is constant. Wherever you take the image, the NDVI ranges will be same. You change the sensor, change the resolution, even in optic, for the same area, the NDVI range on the same day would be different. That is there. Let's say you take the Landsat pixel, you are capturing the image now, you take the Pleiades 30 centimeter image. If you calculate the NDVI, the range would be different. That is there. That's why the data fusion is right now a very active field. And there are many problems reported right now. The algorithm is working with Landsat, but why it is not working with Sentinel-1? Because of that inherent change. The pixel resolution, the NDVI, the stability is not there. Correct. So you have to migrate. So it's active. No algorithm is perfect. You have to keep updated. So with the community, you get a feedback like you did. Let's say you are working on something, you pointed it out. There's someone can take in the active framework. So such studies are there for SAR also. There will be fundamental relation that is going to be there. Let's say for a plant, band 1 will be always greater than band 2. That is going to be the same, but the magnitude by which it is greater is going to change with the sensor. That we have to consider. I hope I have answered your question.
Okay, if there are any more questions, we will have it during the chai session. You can network and ask. There's also his email present here. If you need, you can contact him. We will also put the social media profile. If there is any, we will put it in the Slack group. So you can take it.
So actually I have your slides.
Okay. You can take it. I hope most of us are back. I hope you guys had a really good networking session and chai and samosas. Thanks to the GalaxEye team for providing this. Okay, now let's move on to our last and final presentation. I would like to welcome Tanya. She is an accomplished AI professional who has been actively engaged in industry for 3 years since her graduation with a BTech degree in 2020. At present, she serves as a computer vision researcher at GalaxEye Space. Her work there involves crafting POCs and developing intrinsic in-house algorithms. She merges computer vision and remote sensing data types such as optical sensor. Although Tanya takes pride in their accomplishments, it's the boundless potentials of AI that continually captivates her and fuels her passion for deeper exploration. So let's welcome Tanya. Or present.
Keep it like this on the top. Yeah. Yes.
Check.
So increase.
Full.
So, thank you for the introduction. So, I hope all of you are having a stellar time here at GalaxEye Space, and I'm really thrilled to talk in this topic, which is simply out of this world, INSAR, and is fascinating connections with DEM. So, we just had an amazing lecture delivered by Dr. Akshay on SAR, which definitely made the explanation way easier for me. So, I really appreciate the wonder of SAR. It's like a superpower. The way SAR can penetrate to clouds, look through dark, reveal the hidden secrets of the earth. It's really fascinating. So I really hope all of you also feel that gravitational pull towards this topic, as we all working here at GalaxEye do on this. Right? And I really hope you like this intro. It was a ChatGPT. So yes, moving on. So I've taken a very simple topic which can serve as an intro to INSAR, a DEM generation, which is digital elevation model. So to begin with, all of you can access this presentation from this link. You can take a picture right now, or I can connect with me later on for me to share it. Right. So to begin with, INSAR as a theory means subtracting the phase of two SAR images which are well co-registered, so that their coherence is closer to 1. The more closer it is to 1, the more correlated those images are, and that means the amplitude of both the images are matched for its phase to get the difference, so that you can actually map the difference between two images captured on a different timeline. So the key point to notice from INSAR is that it can potentially measure millimeter scale changes in the deformation over spans of days or years. So I begin with a simple introduction to SAR, so that I can start with this application, so that you can ponder upon this, that how INSAR is actually able to perform all these applications. So first being, it can reveal the active earthquake fault lines. So there are many fault lines. Those are active, some are inactive. So the fault lines which are previously inactive can become active anytime as well. So we need to track those. So INSAR can essentially help you in tracking those fault lines, movement of those fault lines as well. The second one is ice sheets. So as global warming is increasing and ice sheets in the North Pole are repeatedly getting detached from its glacier. So that results in increase of the water, of the sea level. That can also be mapped through INSAR. You can actually track the level of rise and movement of these ice sheets. The third being the magma. So you might have noticed that a lot of naturally occurring hot springs are along the fault lines. That's because of the moving magma beneath the surface. The volcanoes is what the surface of the earth actually separated, and it increased the elevation of the land beneath it. That's how you can track the moving magma as well. The fourth one being groundwater. So at one point when someone is taking out the groundwater from the water from beneath the ground, so the land tends to subside. That is one of the use cases that you can also perform with the help of INSAR. Movement, the subsidence, upward or downward movement, right? So this is one real world example that I took. This is I'm sure most of you remember this Joshimath incident which happened a while back. So the ground has been seen separating, and that is one case of land subsidence. You can see in this image it ranges from 0.0 centimeter to minus 8.9 centimeter. So minus in the plus sign means the uplift or the downward movement, and we cannot say like in the future it has uplifted or downlifted without getting the exact information that which among those two SAR images are the master image. Those in that relation we can say if the previous one image is the master image, then we can say the minus sign means there has been upward movement, and the positive sign means there is a negative movement, like subsidence. So there are two types of radar interferometry mostly here, the cross track and the long track. So cross track here is with the help of single antenna radars, SAR basically, and we perform it with a repeat pass. Like at a certain temporal resolution, we fly the radar again to that region, and we calculate that baseline between, so basically the difference between those two radar images. So the examples that we just saw are from the single pass repeat pass interferometer only. So we can perform topography and we can get the DEM generation and the deformation over the time, the displacement of the land basically. And the second one is a long track interferometer. So basically there is only one system with two radars in it, and it's majorly used in radial motion. We can get the velocity of any object over the ground with the help of this. So in this lecture we're going to focus more on the cross track interferometer with repeat pass interferometer. So this is just a recap. You already had a well explainable session on SAR already, so this is just for a recap. So a SAR signal is comprised of amplitude and the range, and range itself can be disintegrated into different parts of it. One which is caused by the phase, range phase. Basically there are two satellites. One satellite has traveled, the signal from one satellite has traveled more distance as compared to the other satellite, and we call that distance as delta R. Basically, if this is R2, this is R1, then R2 minus R1 is delta R. And rest of the contribution are from the scatters, basically the speckle noise, which eventually get cancelled over the time. When we subtract both of these images, the scattering contribution get cancelled out. This is a visual example. This is the intensity of the SAR image, and this is a corresponding phase information, which you cannot make anything out of it because it contains a lot of noise in it as well. Right. So a basic block diagram for the DEM generation. You get the two co-registered SLC images. You perform interferometric phase map, basically subtract the phases of those two images. Perform interferometric flattening. Basically, if you want to get the altitude information, the relative altitude information, you need to remove that phase contribution that is there because of the difference in the range. That will be made easier down the line. And the second part is phase unwrapping, that I'll also be explaining, and eventually you'll get a DA. Okay. So as I explained earlier, one satellite is traveling R1 distance, and the radar signal from the other satellite is traveling R1 plus delta R. So when we subtract the phases of these two images, we'll get 4 pi by lambda upon into R2 minus R1. R2 minus R1 is characterized as delta R, that difference in the range that one satellite signal has traveled. And 2 pi to consider the whole spectrum, the whole cycle. And we multiply it by 2 so that we consider the back and forth signal. It goes one time and then returns also. So to consider that, the number of cycles it has performed by reaching the ground and then coming back, we multiply it by 2 as well. And divide by lambda, which is our wavelength of the radar signal. It can be for X band, C band, L band, any band. So we saw here that delta phi, the phase change, is 4 pi by lambda into by delta R. So we need to calculate delta R for this consideration. So let's suppose we have two dominant scattering points on the ground, and by dominant I mean we take in consideration that there are just 2 points in these neighboring resolution cells. Resolution cell is basically the smallest distance that a SAR system can make out, can resolve. So let's suppose that there are 2 scattering points on each of those resolution cells which do not change over time. Rest of them will only contribute into the scatters, right? So with the help of similar triangles and the triangulation methods, we can get the approximate value of delta R, which is the extra distance here, -2 into Bn. Bn is the perpendicular baseline from one SAR radar signal to the another. And QS. QS is the slant, perpendicular drawn from the slant range of one resolution cell to another. We can talk about the derivation of this into the references or later on if you want. So if we want to actually calculate the DEM, we need to put the value of delta R in phase change. So as from the previous slide, we know delta R is -2 into Bn QS upon R, Bn being the perpendicular baseline, QS being the perpendicular distance. And if we put it over here, we'll get this value, 4 pi by lambda Bn QS upon R. R is the whole range of one cycle, right? So, so our next step after subtracting these 2 phases is to get a flattened interferogram. So since DEM is what elevation model, we need the relative altitude terrain values from one point on the ground to another. For that, we need to subtract the phase contribution which is there because of the difference of the distance traveled by both the radar, the signal from both the radars, which is delta R. So we can basically disintegrate this whole value into 2 parts. One is with baseline and Q parameters, which is the altitude, if you can say it. The Q is the altitude of one resolution cell, of the neighboring resolution cells, right? And the first term we'll consider of that. Theta R is the incident angle from which the radar signal has traveled to the ground. And the second term consists of the Bn, which is the baseline, and the S, the slant range difference here. So we essentially, and theta is again the incident angle. So we essentially had all of the term in the second part to calculate it. We need to subtract it to get that phase variation, proportional to the altitude difference between 2 resolution points. Right? So after this, we have got a interferogram, a flattened interferogram. So this is one example before flattening, and this is after flattening. If you see the major region there have been more smoothened over time. So our next, so this is our flattened interferogram, but it is again wrapped. Wrapped in sense, the fringes in the interferogram follows a range of 2 pi, -2 pi to +2 pi. So whenever the value of the phase is increased, it goes to the extremes and goes beyond extremes, like less than -2 pi and more than +2 pi, it basically wraps it around. It changes the values. The +2 pi comes to downwards to the -2 pi values, and -2 pi changes to the +2 pi. It kind of wraps it around, like here. So we need to correct this information by multiplying it with the correct pi multiples of the pi values. So for that, we need to consider the altitude of ambiguity as well. So altitude of ambiguity is basically a difference of altitude that is introduced with the change of one fringe to another, right? And a very interesting thing which came from this formula is that it is inversely proportional to the baseline. Baseline is a perpendicular distance, right? So the larger the baseline, the smaller the altitude of ambiguity will be, which is very good to have a high SNR value. There will be high signal to noise ratio for that, right? But this also includes one problem, as if you have a smaller altitude of ambiguity, you will end up having very often of these wrapped signals. So what happens is that, for example, there is a bare ground, right, and suddenly there is a vegetation, there is a forest cover. So if you have an altitude of ambiguity of say 10 meter and the forest cover that standard is of 30 meter, you won't be able to make it out. It will be wrapped again. So that is a trade-off that we need to consider. So the altitude of ambiguity should be enough so that SNR is appropriately high, and it should not be that low that we are not able to map the sudden changes from one resolution cell to another. Right. So this is example of one wrapped phase, and that is unwrapped phase. You can see fringes more smoothing out over the time. They had more number of fringes over here, whereas we don't have any such close-knit fringes over in the unwrapped phase. So for one example, this is the whole steps, like interferogram, we get the phase difference, then we flatten it out, but subtracting the contribution that is there because of the delta R change, and then the unwrapped interferogram. When we perform some unwrapping algorithm, we can do it in Snap as well. Snafu is one of the commonly used unwrapping algorithm. So for this session, we can create a DEM and a displacement map of our own. So there is this platform Vertex, which is provided by Alaska Satellite Facility, that anyone can simply generate their DEM and displacement map from. You just have to follow simple number of steps to get it. I won't even call it generation, you can just access it over there to play it around with, to see how it actually looks like in the real world. So if thought it was going to be an interactive one, so if anyone wants to go to this website and sign into it. Anyways, I am going to provide the link to this presentation anyway. You can go into this. This is an example polygon that I took and the recent mandate. So the step 3 here is select SBAS search to find SLC pairs, which means small baseline subsets. So we can consider one image. We can take one image as master. And simple baseline search would do is provide a number of options that you can choose as a slave to that master image to get the interferometer. So what baseline sample is subset is what do that it provides you a bunch of pairs to choose from. So here the baseline is a temporal baseline, right? So I have a video of that I performed this analysis, the steps to get it. Which we can fast forward to this. Select the Sentinel-1 satellite. Select the time, date. This is your region of interest that we selected. It gives you a bunch of the SLC interferometers. corresponding to your area of interest, and you can select the one. So you see the middle one is the one that contains all of the region. Selected the search type SPAS search. So select any of the date that you want. I selected June 22, 2023 and the June again of 2022. There's a number of pairs that it actually provides. We are selecting our custom pair, we're making it up. These are the data points of the SAR timeline that single one is captured. Just add it and just have to sign in and we'll be ready to download it. Okay. So this is the result that we got from ASF Vertex. So this is the interferometer from June 2023, that is from June 2022. We got the DEM as well from there. And this is the wrapped phase, which you can see it's very noisy. And that is the unwrapped phase, which looks more like the real world image. And the corresponding displacement map. So here it says that minimum displacement is of minus 0.05 meters and maximum is the 0.02. So minus, since I have taken the previous one in the timeline as a master, minus here means there is an upward movement and the plus is the positive means it's a downward movement, right? So extra, basically extra distance that radar signal has to travel, right? So for displacement map that we want to generate from the DEM, this process is called as DINSAR. So this is another variant of INSAR which is called differential INSAR. In this, from the result that we got, we simply subtract the DEM. So if we subtract the altitude information that we have, we'll get the deformation that has happened over the timeline, right? So there are many variants of INSAR that you guys can go and search about, like PS INSAR, which is persistent scattering INSAR, and MD INSAR, multi-dipolar INSAR. But this is something that could serve as a starting point for your research on this topic. So if you guys can go to this link and take the poll, that would be really good. So anyway, these are the references that you can also get. But with this, I'm open with the questions if you guys have any.
Open to questions. Anyone having questions?
How is computer vision?
So currently we are exploring this phase of INSAR itself. So with for the DM generation and this displacement map, computer vision is mostly comes into the picture when we want to do analysis on the top of it and basically the visualization. So there are a number of use cases like landslides. You can use computer vision algorithms to assess and see, okay, this is the different places that has been changed over the timeline. Yes.
You took a long time frame between two SAR images.
Yes,
does it not cause a problem that
yes,
inherently
it kind of cause a problem in sense of the bigger that baseline in terms of temporal sense, the more decorrelation there will be for those images.
But for DM it is good.
For DEM also it's not good. For DEM you want the baseline to be as close as possible. But
temporal baseline should be low or spatial baseline?
Temporal and spatial should be large, temporal should be low. Because you want to get the DEM in the same time frame that you are getting your satellite to move from.
For generating this DEM using interference. So will you use a ground truth high resolution DEM for generation, or will you directly use a range information to get the relationship between phase difference and altitude?
The resolution would not be of much factor over here, since these images were constructed with the help of Sentinel-1, which do not have very high resolution but good enough to be created. Right? For range difference, I didn't get your question on the range.
Are you using any ground truth the DEM model already which is generated?
To map the validation of this. Right now in this we are not, but there are many that can be used, like SRTM could be used, but it's a very old one. There is one from Japanese satellite JAXA that could also be used to validate it.
So one more, if there is a plain ground and vegetation, there will be getting multiples of phases, right?
Right.
Can't we use that information to get the DEM?
So vegetation majorly will cause into volumetric scattering, which will only create the noise. It will not help you in the DEM generation as per se. For accurate DEM generation, you want your ground to be as clean of the vegetation as well. And it also depends on the wavelength of the SAR signal that you are using. If you can see, X-band is a smaller wavelength, it will create more noise. If you see as interferogram, it has more noise in that. As you move towards the upper wavelength, which is L-band, you will get a more clear picture.
So what is the accuracy that we can expect DEM generation from these kinds of interference when compared to other DEMs, other levels?
Other DEMs also are made from SAR design.
No, like
from this ASF that you are talking about.
Like SRTM is basically.
Yeah, it is also interferometric product.
So interferometric, yes. But it's very old one. So it's correct.
Okay. What I'm asking here is what is the accuracy of real ground truth information and the one which is generated?
So in this case, sorry, I just answer it. The resolution that you get is around 50 meters. Even with the SRTM is 100 meters, right? If I'm not wrong.
It is 90.
90 meters.
No, there are two chords. One is 3 arc second and 1 arc second.
Yeah, 1 arc and 3 arc.
Right, 30 and 90, right? So that's the accuracy which we are able to get. Like, of course, if you move into high resolution, right, if I'm not wrong,
I think the absolute error of SRTM is somewhere around 16 meters. 60.
A general rule of thumb they say is that if your spatial resolution is, let's say, x meters, so DM resolution will be 4x meters, something like that. So 10 meter satellites, 40 meter DM.
For SRTM it's 16 meter, close to 16 meter absolute error. Root mean square is around 9.8 meters.
And as for ground truth, right, so this is actually a theoretical model. It's not an empirical model. right? So the values that you are getting are actually coming from physics, and the techniques have been validated.
So SRTM is also a radar DM, shuttle radar topographic mission. So it is also radar. So this is also Sentinel also radar. So you can expect a similar sort of accuracy or absolute accuracy.
And if you want like more accurate, more resolution, then I think either you go with a less resolution sensor or LiDAR people use.
LiDAR is
higher accuracy.
What's the accuracy of ALOS like? ALOS, JAXA.
JAXA's LiDAR?
Yeah, it's not LiDAR, it's also the SRTM kind of product, DEM product.
L-band. It should be.
Is it like less than?
It should be. It's an airborne platform, correct?
Sorry?
No, it's airborne satellite.
Sentinel and others are not launched for them as its main purpose.
Correct.
So this is a kind of, we got a secondary use case of it. So they, most of the validations are done for either what was their main use case was. Maybe we should see the research on it, because again accuracy you want, it's like you have to get some ground data, then you have to do it's like how much so it's like their main purpose was not really a den, but it's kind of one of side use case where you have physical present. From that you can find out the den also.
Any more questions?
When you're analyzing ground truth, how do you distinguish whether a real land subsidence has occurred, whereas what if it's just the increased distance when the satellite is capturing the image?
Your question is, when do you actually validate there's a land subsidence?
Yeah, how do you distinguish between subsidence actually happening versus if there's increased distance between both the signal positions, like when you've taken it?
So there are formulas for that we can account the baseline factor into. That can give us exact values, okay, this should be the land subsidence. And for the ground truth, majorly we tend to go towards the real world data that we can collect to validate it. That's the validation.
Okay, so there are no more questions, we will end it.
How much computation do you need for 1 terabyte?
So, I didn't
How much computation?
How much RAM or how much time you need for 1 terabyte?
For 1 terabyte SLC image to this method, ASF? I'm actually not aware of the RAM contribution.
Is that what is the minimum computation required to do this?
But see, always you don't need to see the series of let's say 25 square kilometer. You don't need to process entire 25 square kilometer. If your RAM is less, you cut into multiple pieces and multiply it. But again, it's like
processing will always happen subsort-wise or batch-wise. So even if you processing then I think it takes more than 1 hour to process a pair of data. So in terms of computation, how will I sell it commercially? Like, my computation will be very high. Is there any way to?
So one way could be to create a time series of it. So you perform this analysis for land subsidence, for example, over a region for a particular time and map it over the time, and you show that this analysis to a client. Okay, this area has been, this point in the ground has been going downwards again and again. That is one thing. But if you want to do it in the real time, you have to consider the computation.
So one example I'll give you, for as you talked about, how is this commercially viable, right? So what people do is they actually derive products out of it, like unwrapped phase, right, wrapped phase, and those are the ones which, so taking example of ASF itself, right, what we get from ASF are these phase products, unwrapped phase, wrapped phase, and these are the ones which we actually use to produce the DEM. So they don't directly sell Sentinel-1 SLC pairs, right? But they give you these products. And currently, I'll give you a benchmark. If you process one order, if you put one request in ASF, it takes around 3 to 4 hours to process the products. Right? So in the back end, they are I don't know what their architecture is, but what is made available to us is just those phase products which are actually easier to handle, because we are not doing the phase derivation part. We're just getting the final product.
Anyway, has to correlate with the cadence of your satellite as well.
Any more questions?
So, with this we can find out groundwater tables, right?
You can find out where land subsidence is happening, and with another data set where you can map, okay, these are the regions where groundwater has been taken out. Then you can assess it. Okay, this is the groundwater is the reason, that's why the land subsidence is happening here. You cannot just go ahead with, okay, this is the ground subsidence. If you groundwater has been taken out from here just based on this land subsidence, you need additional data sources.
But you want to talk about that satellite, gravitation satellite, good point.
Grace.
Yes.
I think I've forgotten, that was a very long time, but yeah, there are like two set of satellites in Grace, if you have heard about it, two set of satellites. So they constantly measure the gravitational pull. So if there is a land subsidence at a ground, so this satellite, there are two pairs of satellites there. So the first satellite, which moves over from the land subsidence part of the region to another, it will be slowed down a bit, right? So, but the second satellite has been moving on the correct velocity, right? When it then comes over to that land subsidence part, it will then get reduced. The speed will then get reduced. So that's how the Grace is actually able to map, okay, there is the groundwater changes happening in the ground, or maybe some another shifting of the earth region or crust below it. You guys can look it up. It's very interesting.
More questions, guys? Okay, thank you. Okay, thank you, Tanya, for sharing your insights with us. It was really useful. And also I want to thank GalaxEye and team for giving this space and giving us chai and samosas. Also thank you for our speakers taking time in their busy schedule to prepare this, come over and present your insights to us. And also a huge thank for the participants. Without you, this would not be possible. Like we are in the 9th Let's Talk Spatial event. The next one is going to be the 10th. We created 10 as the benchmark and we are going to achieve it. So we are really happy in doing it. And I would like to welcome Gautam to announce, to say about our 10th Let's Talk Spatial event.
Hi everyone, once again to introduce myself, I'm Gautam. I think it's not. I'm audible, right? So I'm a part of a company called as SkyServe. Has anybody over here heard of SkyServe? Okay, so we are about a 3-year-old startup. So we have a edge computing platform. So we are looking to foster, along with Let's Talk Spatial, a developer community. And so basically we want a lot of developers to come with their models, classical JIS or GeoAI models, which could be directly deployed to, basically onboard the satellites and where we can generate insights directly from there. Now this is basically democratizing the whole Earth observation industry because a lot of time and money and efforts are spent in acquiring a lot of satellite imagery, and the whole supply chain is basically fragmented because of that, and we're trying to solve for that. So the next event that we have will probably be talking around more of this, and maybe we're not yet decided on the exact theme yet, but we'll try to put it around it. If anybody wants to speak on that, you guys are invited. So the event will be towards the last week of July at our office at SkyServe in Chinagar, 4th block. And we are also looking at a sort of a hackathon of similar kind, and this event is going to be a sort of precursor event for that hackathon. So I don't know how that is going to pan out, but yeah, all of you are welcome to come out in much more numbers than today to that event, and so that we can connect with you and tell you more about what we do and how you can benefit from it. Also, as an individual developer, how you can become a sort of solopreneur also. So more about that maybe on during the event we'll talk about it. Right. So yeah, that's about it. Thank you.
Yeah, so I think no, just closing notes. I just want to put a thank you note for turning up. Yeah. No, I know the sitting for 3 hours and kind of paying attention to everything. This was.
Pushing everyone.
I am looking there. I thought the camera is there, and then suddenly it changed. Okay, yeah. So, thanks for turning up. And if anyone is interested to talk about INSAR, SAR, satellite, please feel free to drop by in our office. We are more than happy to respond. Really thankful to Dr. Akshay, Tanya, Soumya, right? Thanks a lot. We learned a lot from you. I personally learned a lot from all of you guys. Lovely to have you here. And yeah, if you guys have any feedback, you want to talk about anything, discuss with me, or have more samosas, please feel free. Thank you so much. And also a huge shout out to our Let's Talk Spatial organizers as well, to their efforts in arranging everything.
Okay, so yeah, just now you saw like how we are organizing. Like we got in a pitch in for Let's Talk Spatial 10th event. Participants from here, if you like to host us, do approach us. I just want to say again, like there's a Slack group. Do join that. We have many channels. You can look for internships. You can look for resources. And also we are having GitHub where we will post the presentations from the speakers, so you can follow and get the presentations and also get notified about the future talks. And future speaker, if you want to present something, do approach us. We will also try to like contact you, like seeing your social media profile. But again, if you are willing, we are most happy to like have you as a speaker. And since the next Let's Talk Spatial event is the 10th event, we are planning to do something like creating a sticker or doing something. Still we didn't plan it. So if you are having any idea, do share it with us. We will try to do it. And there's a stickers from GalaxEye also. Do take it and appreciate the effort to like create it. And yeah, that's it, guys. So it's for networking and the group photos.